Dear students, after having finished this conditions CR equation necessary and sufficient conditions for a complex function to be differentiable or to be analytic, we now turn to complex integration. That means integration of complex functions. This integration of complex functions is a unique thing. It has its own unique features which do not have any parallel in real and this integration. In both cases, the integration that we are talking about will be Riemannian integration, and this Riemannian integration that most of you are familiar from your 11th class physics, when you discussed work done by force and then taking the work done as computing the work done by the area under force displacement curve. You have been, since that day, you have been well familiar with Riemannian integration. The other type of integration that we don't have that in our syllabus, and we shall avoid that because we first would like to finish our syllabus. So, but even before taking up this complex integration, as you will see, it has some unique features. Before that, it is a must that we are equipped with a theorem that is called Stokes theorem, or it is two-dimensional equivalent Green's theorem. Stokes theorem. Those students who already know this Stokes theorem or well this aware of this Stokes theorem, they can skip this lecture. However, if they want a conceptual basis of Stokes theorem, Green's theorem, then they can go through this lecture because it doesn't use mathematics, this complex mathematics. It basically uses intuition in arriving at this theorem. We start with, in order to make things less abstract, we will take help from Ampere's law of magnetism, magnetostatics. I'm not talking about magnetodynamics. Now, in Ampere's law, we have seen that if you remember that, suppose you have, imagine this point that I am showing here. Imagine there is a wire, straight wire, going up, going up from the screen, upwards from the screen, and it carries a current I, a steady current I. It will produce a magnetic field around it. That magnetic field will be in the form of these these magnetic field lines. The circulation order of circulation can be easily found by right hand thumb rule. You just have to imagine holding the wire with your right hand thumb pointing in the direction of the current, then your fingers will curl in the direction of the magnetic field. And so this is, say, let me show some magnetic field lines. These magnetic field lines have a property. The property is that they all go around their source. This is their source. This is the source. And they circulate. We say that they circulate around the source. They go around and around the source. Compare it with electric field due to a point charge. Suppose you have a point charge and here is the electric field due to this point charge. Electric field lines do not have any tendency of going around this source. They simply leave the source. They are simply more eager to leave the source than to turn around it. We differentiate this property of these two fields, electric and magnetic fields, by saying that magnetic field has a tendency to go around its source, and this tendency is given the name of circulation. We say that this magnetic field has a circulation around its source, whereas electric field does have no circulation around the source. This electric field, I mean, there is another type of electric field that is generated when magnetic field changes, that does have this property of this curl, the circulation, but we are talking about this electrostatic field. Anyhow, let us go to this magnetic field. Now we want to measure how much circulation this field has around this source. In order to measure that, we need to remind ourselves that dot product of two vectors is a measure of their parallelism. Suppose we have A dot B. A dot B is a measure of parallelism between A and B. How that is measure of parallelism between A and B? You can see it from this diagram. You have suppose a vector A, then vector B like this, and the two are parallel. No doubt about them. The angle between them is 0 degree, and parallelism is maximum. Parallelism is maximum. Now, we call this parallelism, we say that the dot product is maximum. By dot product, we mean their parallelism. Dot product is a way of measuring this parallelism. Now, suppose you have this situation. You have this vector A, and then you have vector B like this. Now, on the face of it, you will say that these two are no more parallel. They have no parallelism. But since B and A are vectors, there is still parallelism between them. Of course, less than this, but there is parallelism. How? Which type of parallelism? See, B can be resolved into two components, a horizontal component and a vertical component. Now, one part of B is still parallel to A, that is, it is horizontal component. So there is parallelism here, but the parallelism is lesser than this. Then if you now increase this angle, B is now here. It is horizontal part decreases. The parallelism between these two decreases. Again, when you go to this situation when B is perpendicular to A, since a vector does not have any component in a direction perpendicular to it, so B will have no component in this direction, and there is no parallelism. That means theta is equal to 90 degree, means parallelism 0. Now call this parallelism dot product. Then in terms of dot product, we will say that these two vectors have maximum dot product, means maximum parallelism. These have lesser dot product, these have still lesser, and these have 0 dot product. Now, having said this, we can, of course, we should check other angles as well, and then we will find one interesting thing, that the dot product varies in the same way with angle theta. Of course, you see that dot product depends upon the angle. It changes with the angle, and it varies with the angle in the same fashion as cos theta varies with the angle. Cos 0 degree is maximum, cos 90 degree is 0, and other values of cos, if you take any other value of cos theta, that varies in the same way as this dot product. So we say that this dot product between two vectors A dot B is directly proportional to cos theta, and then dot product is also directly proportional to magnitudes of A and B. Why simple? For the simple reason, just as you saw, our concept of dot product here is such that we say that the dot product between these two is so less. Dot product between these two is maximum. These two is less. These two is still less. You must have noticed that the smaller the length of this component, the lesser the dot product. This means that if you take two vectors like this, A and B, like this, they are parallel, they have a dot product. But if you take now these two vectors of more this greater length, these two also have a dot product, but that will be larger than this, simply because, not because of the angle, but because of the lengths, because of the magnitudes. So we combine all this and we reach at this conclusion that dot product, that is parallelism between two vectors, is equal to A, length of this, and angle theta, cos theta, cos theta. So suppose now let us go back to this situation. We have this is the wire running through this, running perpendicular to the screen and in the upward direction. Now current I is flowing there, and this current I is creating magnetic field all around itself. We want to find, for example, there is a magnetic field here. This magnetic field is pointing in this direction. Here it is pointing in this direction. Here it is pointing in this direction. So at every point of this magnetic field line, we have a magnetic field pointing in a particular direction, pointing in this direction. So here like this, here like this, and so on and so on. These are, say for example, I show magnetic field here. It is like this, and so on. Now, how to find this I should say circulation of this magnetic field around the source. For that matter, we take help from an imaginary loop around this. We take an imaginary loop. Say, suppose this is the source I, and we take a loop of any shape. Suppose, for example, this loop goes around this source. That we know that this loop goes around the source. Loop should be oriented, and usually what we do in case of this Ampere's law, the orientation of the loop is determined by right hand rule. Right, what right hand rule tells us? That it tells us that hold your hold this, so the wire in your right hand with the thumb pointing in the direction of the current, then the direction in which fingers curl, that will be the direction orientation of the loop. This means anti-clockwise, simply anti-clockwise. We can also make a rule that the orientation will be anti-clockwise. So anyhow, you have to have an orientation, otherwise this will lose its meaning completely. Now, what about this loop? We are sure about this loop that it goes around the current. And here we pretend that as if we don't know whether magnetic field does it go around the current or not. So we will do this thing. It is something like this. A person X, we are sure that he is going from Srinagar to Jammu. We know that he is going from Srinagar to Jammu. And we want to know whether another person, Y, goes from Srinagar to Jammu or not. If someone says you that I have seen Y with X, and X was going from Srinagar to Jammu, so naturally Y is also going from Srinagar to Jammu. Something similar we are using here. We know that this imaginary loop is going around this source, and then this is going around the source. And if magnetic field also goes around the source, then magnetic field certainly has a circulation around the source. Now, how will we determine whether magnetic field is going around is going along with this loop? So we will do this thing. Take any point on the loop, and this loop here, and divide this loop into small elements of length dl. Small elements of length like dl. These small elements all along the loop. Now, consider one element of this loop, dl, and look for the magnetic field at this point where this element is located. The magnetic field is, say, in this direction. This is the direction of the magnetic field. So we have loop element dl like this, magnetic field like this. There is parallelism between the two. Hence, magnetic field is parallel to dl. Suppose it had been like this. Loop element is like this, and magnetic field is like this. Then magnetic field is not having any parallelism with dl. Dot product is 0 here. And for this case, for example, suppose now dl is like this, and magnetic field is like this. Now in this case, magnetic field is neither completely parallel to dl nor completely perpendicular to dl. So magnetic field has this some dot product with this. This means that it is parallel to dl, but the amount of parallelism is lesser as compared to this case. this case. So dear, what we do at each point along this loop, we calculate parallelism between B and DL. Parallelism at one point is given by this B dot DL. B dot DL gives us the parallelism at one point. Now we add up all these parallelisms. Then we go to another point, find a parallelism there. Then we go to another point, find parallelism there. Then we go to another point, find parallelism there, and so on, completing this whole journey. And then we add up all these little parallelisms, and we get B dot DL, total parallelism. Now, along this loop, since this is loop basically a closed curve, so we put this circle here and write the name of the curve here, and we say that this quantity is a measure of, it measures how much circulation there is in magnetic field around the source. I think this is clear now. They say that there is another way we can measure this magnetism, this parallelism. What is that way? If we do one thing, if we divide this loop into, this is the area, this is the area enclosed by the loop. And if we divide this area into smaller and smaller elements like this, smaller and smaller elements like this, see, I am dividing area into smaller and smaller elements like this and this, this and this and this. You can see. Now, if you now do one thing, if you calculate circulation around this one particular loop, smaller loop, I have divided this whole area into a number of loops. Take one loop here, small loop, and find circulation around this loop, total circulation around this loop. Circulation around this, when you now, let us go to another page. We have the loop here. This is the loop, and then we have divided this loop into little area elements, a number of them, area elements. These are the area elements. Say they are not so big as I am showing. I am showing them big only to make them clearly visible to you. Suppose I think of this. Let's take this loop 1, then loop 2, loop 3, loop 4, loop 5, loop 6, loop 7, loop 8, loop 9. This is different. Consider first loop 1. This is, I will show you here this loop 1. Now, if I traverse it in anti-clockwise direction, I will go this loop 1. I will go like this. I will go like this and calculate circulation around this loop. Now I go to loop 7, which lies below it. Loop 7. Loop 7 is here, below it. I have to go anti-clockwise in this loop as well. When I go anti-clockwise, I traverse this. The common side between them is now traversed in the opposite direction, and naturally you're traversing it in opposite direction, and then this like this. When you add up these two circulations, this circulation will cancel out, and you will be left with this loop, this loop, this loop. Now this loop has this story. This is the story. Now I mean, it was 1 and 7, 1 and 7. Now 7, 1 and 7. 1 and 7 have adjacent loop here. That's 2 and 3. 2 and 3. Same will happen with 2 and 3. Now when you take this 2 and 3, and when it becomes a single loop, it is again traversed in anti-clockwise direction. So this line will be traversed in anti-clockwise direction, and when we add up these circulations, this will go. If we go on repeating this, then we will find that these boundaries between these loops, they will dissolve out, all of them, until you reach the end loop. For example, here is one end loop. This boundary cannot be dissolved. It can, because it doesn't have any loop on this side. So ultimately, this out of this is saved. Simply this will be saved. Simply this will be saved. It means that the sum of all the circulations in this surface, sum of all the circulation around these little loops is equal to the total circulation around this. Total circulation around this B dot dl is equal to, that is equal to sum of all little circulations. Now circulations. Now let us consider this situation. Let's consider this situation. We will keep this in our mind and then let us go here. Suppose we have, this is x-axis, this is y-axis, x and y, where we are in confined to a plane, and z-axis is above this screen. Above the screen, x and y are in the plane of the screen. And suppose, think of a small, light, very light wheel. You have a wheel like this. These are spokes of the wheel spokes, and this is here. Imagine a small little handle upward, which is up in upward direction handle, and you are holding that with in your hand. You are actually doing one thing, that suppose there is water flowing here. Suppose water is flowing in this direction along y-axis. Water is flowing along y-axis. Okay, and you lower this wheel and place it in the water. In the water, you have here this wheel. Wheel has been placed like this. This is the wheel. The handle of the wheel is in your hand. You are holding the handle of the wheel. Now, if this velocity and this velocity, if these two velocities are equal, then the wheel will not rotate. It will not rotate at all. See, because this when water flows like this, it is pushing these spokes of the wheel in this, which direction? Let us see which direction it is. It is pushing it in anti-clockwise direction. But if you consider now this, forget about this and consider this. This is pushing it in this clockwise direction. If the two velocities are equal, then the net force on this will be zero. Net torque on this will be zero, and it will not rotate at all. It's not going to rotate. Okay. Now, having said that, suppose now this velocity is slightly more than this. That means there is a, if I call this velocity v, and what I'm actually telling you, that the velocity itself, velocity is directed in the y direction, vy. I write vy because it is in the y direction. If velocity in the y direction is changing with the x axis, with x, if it is changing with x, that means at this x velocity is less, at this x velocity is more. If there is this thing, that velocity is changing with x axis, with x, dv by dvy, vertical velocity, that is y velocity, is changing with x like this. Then now again place the wheel here. You place the wheel here. What will happen? Now you know there will be a net torque on the wheel that will be counterclockwise or anti-clockwise, and the wheel will start rotating. This causes rotation. This variation of y component with x component. Variation of y component with x component. It reminds me of from my childhood. I've been whenever I write something like this, it reminds me of a person who has cross vision. He is looking to the left with his right eye and to the right with his left eye. Now, having said that, suppose now the velocity of the fluid not only has vertical velocity, a component that is vertical, that is y component, it also has a horizontal component. So that means suppose the stream is flowing in this direction. If the stream is this, if this is the stream, then it certainly has a horizontal component, it certainly has a vertical component. Now we were considering a vertical component. Now let's take horizontal component. Suppose now we have this situation. There is fluid velocity here is v, fluid velocity here at the top is v. That means velocity of the fluid at the bottom and at the top is v. Both velocities are now x velocities, x component, x velocities. Now place wheel here again. Place wheel here. The wheel will not rotate because this will try to turn the wheel in clockwise direction. This will try to turn the wheel in anti-clockwise direction. Wheel will not rotate. But see, if this is lesser, this is more, this velocity is more, then the wheel will turn in a clockwise direction because of this. Now combine this and see what will happen. Combine this and see what will happen. The wheel, you have the situation like this, and this horizontal velocity, x velocity changed with y, and y velocity changed with x. Here is this situation. Place the wheel here. This is the wheel. These are the spokes of the wheel. Okay. Now see what will happen. You will find that this there will be a net force, net torque due to these two in this direction, counterclockwise, and torque due to these two in this direction. That means if there will be any difference between these two torques, then only wheel will rotate. If there is no difference, then wheel will not rotate. This means that the tendency of the wheel to rotate will depend upon this del Vy by del x, minus del Vx by del y. This tends to this is del Vy by del x. This tends to turn the wheel in anti-clockwise direction, and this tends to turn the wheel in clockwise direction. The net torque on this will be this. We say that this is curl. That means that velocity has a tendency to turn. A wheel, and you can think of a wheel and then say velocity has a tendency to turn. Similarly, vector fields have these tendencies. This tendency, now look at this. This is interesting. If the wheel turns, suppose the wheel turns right like this, wheel turns counterclockwise like this. What it is actually rotating about? Identify the axis around which it is rotating. It is rotating about z-axis. Imagine z-axis here, and it is rotating around that z-axis. So we say that this is curl, component of curl around z-axis. We call this a k. We say it is k component of curl. Similarly, if you have this vector field that has three components, Vx, Vy, Vz, three components, then you can calculate its tendency to turn around all the three these axes. For example, when you imagine this, when you calculate tendency to turn around z-axis, you get this. When you are talking about z-axis, and see, there is no z here. Velocity with this is the component of velocity in y direction. This is y x displacement, x component, y displacement, z is not here. Similarly, when you compute j, you will get, in case of j, you will have no j, no vy or y there. In that place you will have x, you will have z there, and you will have z and x. And similarly around this this I, you will have no x there, only y and z. The total total curl is then determined by this del cross v. This measures total curl. You can see how you can yourself now understand why it is curl. I, j, k. This is the way we write cross product between two vectors I, j, k. Then these components of this gradient, we have that component x component d by del by del x, y component del by del y, z component del by del z, and then we have vx, vy, vz, this component vz. Now if you expand this, you get ith component, that these are to be deleted, and we get del vz by del y minus del vy by del z plus j. If you write plus j, then you will have to do one thing. You will have write plus j. Now what you do, you don't go from this to this first, you go in the reverse order, because actually j comes with a minus sign, but I am writing it with plus sign, so I will have to take it this into this first. Del v x by del z minus then del vz by del x. Now you understand what this means. Now k is your k that we explained actually in detail. This k is like this. Del, you have del vy by del vy by del x, and then we have del vy by del x, del vy by del x, and del vx by del y. You have already seen what we mean by this. What is this term? Why this minus? Why this? And similarly, you can think of this. This is the total kernel. Now, since this is kernel measures the rotating tendency, it seems to be same. Its meaning seems to be the same as that of the circulation. In fact, this is same. There is a difference. Of course, there is a difference. What that difference is? The difference is that kernel is basically circulation density. It is the density of circulation. That means density of circulation means circulation per unit area. Circulation per unit area of that surface that we were discussing. This let us go back to this. It is circulation. Kernel is circulation per unit area. Now this will not be treated as kernel. Kernel will be if this is unit area. And better, what we do, we imagine that this area now starts decreasing. That means del A starts decreasing down to say 0. It becomes dA. And when area decreases, the ratio of this circulation by area, that tends to a limit. Circulation by area, because as area decreases, circulation also decreases. However, the two, if they tend to a limit, that limit is called kernel. That means you can simply understand, think of kernel as this. Kernel is, for example, kernel refers to a point, while a circulation refers to a loop. So kernel at this point, kernel at this point, kernel at this point, kernel at this, kernel at this point, 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 kernel at this. If you add up all these kernels over this surface, then they will give you this total circulation, because as you have seen how they give us total circulation, the intervening these boundaries, they melt down, and we are left with this the final boundary. So we have a beautiful theorem here, a very beautiful theorem that tells us that circulation around a closed loop, and circulation we measure it by this B dot dl. Circulation around a closed loop is equal to surface integral of, it is not closed, sorry, surface is not closed. This surface integral of, we write it, there are two ways you can write this. Some people write two integral signs, call it double integral. Some people simply write S or some other this and sometimes they write del V, surface bounding some volume, but here there is no question of volume. We will continue with this simple notation. This This is surface integral. This is loop integral. This is surface integral of the curl of this B dot dA. That means imagine this to be this circulation per unit area multiplied by area, that is total circulation. You can also understand this like this. This is curl at a point. Sorry, we go back to this. And then this is curl at a point. We're talking, yes, curl at a point. These are the points. Curl at point. We're adding up all these curls. We're adding up, and we get this loop. Then this beautiful theorem, this beautiful result is known as Stokes theorem. It is true for these vector fields. Vector should be continuous. Of course, it should be continuous. And see, we have we can instead of although we have derived it, we should, if we can call that derivation, although we have conceptually derived it for the case of a magnetic field, it holds for all the vector fields. So if I write a general vector field by say w dot dl is equal to, then w dot dl is equal to this, sorry, w dot dl is equal to s del cross b, that is del cross w dot d a, the area element. Okay, this is vector. Curl is always a vector, and this must be vector. Of course, this is a dot product. We also take here dot product. So this Stokes theorem basically converts a loop integral or a line integral. This is a closed loop. We have taken this, if you remember, this was the current and this was the loop. But the surface, say, we cannot say surface is closed. Surface is not, it is bounded, not closed. A closed surface would be, say, surface closed within a volume. But we are not talking about anything here about volume. That is the case with Stokes theorem. Gauss's theorem. I'm sorry. I will be using this theorem, but in a simple case, in a simple form, that's called Green's theorem. Green's theorem is Stokes theorem in a plane. Instead of 3 dimensions, we will be taking only 2 dimensions. We will think of this, that this W has one component, the Wx I plus W y j and 0k, no z component. Same will be the case with dl. This displacement dl will be having an x component, that is say dx I dx plus j dy, but 0k 0 dz. If I use this, suppose I use this here, the theorem becomes even simpler. Stokes theorem is this W dot circulation W dot dl is equal to circulation around a closed curve is equal to loop integral, is equal to surface integral of del cross v del cross w dot dl dot da, area element. Now I have let me use this w is equal to I u wx plus j w y plus k wz, that is 0. Similarly, we have this dl length element, small length element, I dx plus j dy plus k dz, 0. Now take this dot product of them, dot product w dot dl, that will be dot product wx dx. In dot product you multiply only same these terms, not cross terms. And this is w dot, this will be wy dot dy. Okay, now this is the dot product. Then, so far as curl is concerned, w dot w cross del cross w, that will be I j k w x w, first this d by dx, d by dy, d by dy, d by dz. Now d by dz is 0, that is 0. Similarly, I have wx, wy and 0. When I compute this, I will get, see, if I take I, look here, this will be 0, this will be 0, so no I. Now minus j or plus j, this and this will go. I will have this 0, again 0, and then k plus k. I will have, in this case, k is equal to k into only z component. This will go with this. I have del wy by del xc, y divided by x, the same old component that we used in understanding this, minus del wx by del y. This is the, now if I substitute this, substitute these values here on the two sides, I will find that first of all I have this wx dx plus wy dy, wx wx dx plus wy dy, wy dy, okay, is equal to, we have here on the other side we have surface integral, and we have del cross w is k, this see what I am going to do, that is k del w y del x minus del wx del y dot, I have dot dA. Instead of dA, I will write dx dy, dx dy, but with direction. Area has a direction that is normal to the plane, and cap normal to the plane. K is also normal to the plane. It is in the z direction, our plane is in xy direction. So this is normal to the plane, this is normal to the plane. Dot product of two vectors which are parallel, is simply equal to the this numerical product, and then it means that we have this theorem done. Now dwy by dx minus dwx by dy into dx dy, while I have taken k dot n unit vector, that is just one, simply a number because it's dot product. So this is the Green's theorem. In our next video, we will now go for Cauchy's theorem. We will discuss the unique things associated with this integration, this complex integration. Very interesting things are lying ahead, and we hope that we will enjoy them. Mathematics is another name of beauty, and that beauty is revealed well by Cauchy's theorem. You can yourself see when you understand that. Thank you so much.